At this point, we've talked a bit about gravitational forces and about electrostatic forces, and we've noted some similarities and differences between them. One of the important similarities is that they can both be exerted on objects that are not in contact. And this sort of irked some scientists early on. They thought it was weird that two objects could put a force on each other without actually touching each other. And that's one of the reasons why scientists started to explore the idea of fields. The general idea with gravity, for example, was that rather than the Earth magically somehow pulling on all things that are near it, the Earth creates this invisible thing around itself, almost like a net called a gravitational field. And it's that field that pulls on the things that are around Earth. So even though the Earth is not in contact with all the things it's pulling, Earth's field maybe is. And that was a compelling idea a lot of scientists found. Turns out there's a lot of other good reasons to consider the idea of force fields, and we'll get into some of that today. So in keeping with the idea of drawing parallels between electrostatics and gravity, let's look at some of the similarities between gravitational fields and electric fields. So the idea with gravitational fields is that any object with mass will create a gravitational field. And similarly, any object with mass will be affected by a gravitational field. For example, right now the Earth, which has mass, is creating a gravitational field. And you, who have mass, are being affected by, you're being pulled by that gravitational field. And that actually works in both ways. You, because you have mass, are also creating your own gravitational field. And Earth, because it has mass, is being affected by your gravitational field. So this works in both directions. Everything with mass creates its own gravitational field, and everything with mass is affected by other gravitational fields. This idea carries forward to electric fields as well. Any object with electric charge will create an electric field. And any object with electric charge will be affected by an electric field. And when we say be affected by, we really mean will experience a force. Okay, so I like to start with these statements because they, in my mind, lead us nicely into the formulas we have for gravitational fields and electric fields. So let's look at those next. For gravitational fields, we had a couple of formulas. We had this one. And this formula told us that an object with mass will create a gravitational field around it. So in this formula, the M you see here is the object creating the gravitational field. Now, there's one other formula we have that has little g in it, gravitational field in it, and that's this one. So the m in this formula is different from the m in this formula. This first m was the mass creating the gravitational field. This second m down here is a mass that's being affected by a gravitational field that already exists. Now, with this first formula, we didn't put any vector hats in here, even though gravitational field is a vector, because we said, or basically effectively what we did, was we used this formula just to find the magnitude of the gravitational field, and the direction we figured out on our own. And with gravitational fields, that's pretty straightforward. It always points towards the object that's creating it. This formula down here, however, can be used with vector hats on the G and on the FG. Gravitational field will always be pointing in the same direction as the force. So if we're talking about the gravitational field of Earth, little g will point towards Earth, and the force it exerts on anything will be towards Earth. If we're talking about little g on the moon, the gravitational field of the moon points towards the moon, and the force it exerts on any objects nearby will also be towards the moon. So if little g is positive, Fg will be positive. If little g is east, Fg will be east. Those two will have the same direction. And that's because mass is always a positive number. If mass was allowed to be negative, then we would see a case where G and Fg could actually have opposite directions. For example, if little g was down, which it generally is around Earth, but we had an object that had negative mass, well, down multiplied by a negative number would actually give us something that's up. So gravity, the force of gravity could actually be up, even though the gravitational field is down, if I had an object with negative mass. However, there's no such thing as negative mass, but there is such a thing as negative charge. So let's look at the counterpart formulas for electric fields. So just like over here, we had the formula for an object creating a gravitational field. Here we have a formula for an object creating an electric field. And whereas gravitational fields are created by mass, electric fields are created by charge. And then we have a second formula for electric fields that looks a lot like this formula down here for gravitational fields. the force created by an electric field is equal to the charge of the object that's in the field multiplied by the field itself. And just as we had in the gravity case, this is the object affected by the field. And this is a pre-existing field, meaning it's not the field that's created by this object. This is created by something else. It already exists before this Q came along. This second formula also tells us some useful stuff about units. So in the gravity situation, M was in kilograms, force was in newtons, so little g had units of newtons per kilogram. Using that same logic over here, this force, electrostatic force, is going to be in newtons, like all forces. Charges are measured in coulombs. So if I rearrange for electric field, I'm going to get units of newtons per coulomb. Okay, so that, I think, gives us a good intro to the formulas that are relevant for electric fields and also compares them to their equivalent for gravitational fields. The big picture here is we have formulas that tell us about the fields that are created by objects, either the gravitational field created by a mass or the electric field created by a charge. And we have formulas that tell us about how objects are affected by electric fields that already exist. Either how a mass is affected by a gravitational field that already exists, or how a charge is affected by an electric field that already exists. Now, one thing important I want to point out, we said over here that gravitational field always points in the same direction as the force. And that's because mass is always positive. If we had such a thing as a negative mass, then even though Earth's gravitational field is pointing down towards it, we could have objects with negative mass actually feeling a force up away from Earth. Well, in the case of electrostatic fields, we don't have mass over here, we have charge. And there is such a thing as negative charge. And indeed, that leads to exactly the behavior we were just talking about. You can have a situation where the electric field is pointing, say, to the right. But if the charge in that electric field is negative, then the force will actually be to the left. You can think of it as negative right is equal to left. More on that in a little bit. So let's look at how to maybe draw some electric fields now. And again, we can compare them to gravitational fields. Just like we can draw gravitational fields using arrows, we can do the same for electric fields. Remember, gravitational fields always point towards the mass that created them. Because gravitational fields always pull. But with electric fields, it's a bit different. Electric fields can push or pull. So how do we decide on the direction to draw an electric field? Well, this kind of touches on what we were just talking about with this formula up here. We say an electric field points in the direction the force would be on a positive charge. So if we have a positive charge Q, electric field and the force that charge would feel are in the same direction. So let's use that idea to draw some fields here. First of all, let's draw the gravitational field created by an object with mass. So let's say I've got an object over here. This has some mass. And we've drawn this before. The gravitational field is going to look roughly like this. And then what that means is if I take another object with mass and I place it somewhere around here, it'll feel a force in the same direction as the field is going. And remember, one thing we said about these field diagrams is they don't just convey direction, they also convey magnitude. So these areas where the arrows are really close together, like here and here and here, that means the strength of the gravitational field is very strong. In areas where the arrows are far apart, like here and here and here, those are areas where the field is very weak. So we say that the density of the arrows represents the strength of the field. And that's going to be true for our electric fields as well. Another word for these arrows is they're called field lines. Okay, so now let's look at a positive charge. So instead of an object with mass, I've got an object with some positive charge. And let's look at the field it will create. Well, it's going to look very similar, but we got to figure out the direction. And we said the electric field points in the direction the force would be on another positive charge. So if I were to have an imaginary positive charge up here, which way would that guy feel a force from this guy? Well, we know that charges with the same polarity repel. So because these are both positive, they would be repelling each other. So that means the field created by this first one is going to be up. Up is the direction that the force would be on a positive charge. And then we can use that same logic to realize that no matter where I put a positive charge, it's going to be pushed away from this, this positive charge in the middle. So my field lines are all going to be going away. Okay, now let's look at a negative charge. Again, the picture's going to look kind of the same as we're used to. It's just the direction I have to think about. So for the direction of the electric field created by this charge, I have to think of the direction the force would be on a positive charge. So let's say I take a little positive charge and I put it up here. Well, because I now have charges with opposite polarity, one positive and one negative, they are going to attract. So this little positive charge is going to feel a pull towards the negative charge. So that means my electric field goes towards the negative charge in the direction the force would be on a positive charge. Okay, so let's kind of look at the overview of what we have here. The fields created by a mass, a positive charge, and a negative charge all basically have the exact same pattern. It's just the direction that matters. In the case of a gravitational field, the field points towards the mass, which is the direction the force would be on another mass in that field. In the case of a negative charge creating an electric field, the field points towards the negative charge, which is the direction the force would be on a positive charge within that field. Right. This is positive mass. This is a positive charge. Now, in the case of the field created by a positive charge, the field actually points away from the charge because that's the direction the force would be on a positive charge placed within that field. So the direction of the electric field is the direction the force would be on a positive charge. Now, so what happens if we were to have a negative charge in this field? Well, remember our formula up here. If Q is positive, then force will have the same direction as electric field. If Q is negative, then force will be in the opposite direction as the electric field. So if, for example, the electric field is up, and then I multiply that by a negative number, that means my force will be down. So let's kind of draw that in on some of these diagrams. If I were to take a negative charge, say, and put it over here, it's going to feel a force in the direction opposite this field. The field is going away, so the force will be towards. If I take a negative charge and put it over here, again, it's going to feel a force in a direction opposite the field. The field is going towards, so this guy's going to feel a force going away. Now that jibes with what we know about Coulomb's law, right? Here I have a positive charge and a negative charge. They should be attracted, so that force makes sense. Here I have a negative charge and a negative charge. They should be repelled, so that force makes sense. So now let's use these ideas to solve a couple of problems. First example. We have a negative charge, -2 microcoulombs. And we are looking at a place where that charge is experiencing an electric force to the right. because of a pre-existing electric field. So let's draw this out. Here's my charge. It's a negative charge. And it has a charge of -2 microcoulombs. So negative charge, magnitude of 2 microcoulombs. And you know what? I'm just going to put that negative sign down here instead because I think that makes things a little more clear. So I have a charge. Its charge is -2 microcoulombs. And it's experiencing a force to the right of 5.3 times 10 to the -4 newtons. So we want to know what the electric field is that's causing this force, right? Here I have a charge in a pre-existing electric field, and it's feeling a force. So that's basically this formula up here that I'm working with. The force on a charge in a pre-existing electric field. Well, if the force is to the right, and the charge is negative, that means the electric field must be to the left. And that should jump out at us, even if we just plug some numbers in here. So for the force, I have 5.3 times 10 to the -4. For the charge, I have -2 times 10 to the -6. And electric field is what we're solving for. Now, because I've got a vector hat here on top of this force, that means I should very intentionally make it positive or negative, depending on its direction. So I'll actually add that in here. This is very intentionally a positive 5.3 because it is going to the right. So if I then solve this for E, for the electric field, I get -265 newtons per coulomb. So because my force was going to the right, it was a positive number, it makes sense that I ended up getting a negative number for the electric field. And that kind of jumps out from this formula up here. So a better way to write this would be 265 newtons per coulomb left. So although it's maybe not drawn in our diagram here, although we could add it afterwards, there must be an electric field pointing to the left up here. And that's why this charge placed in that field feels a force to the right. Let's look now at the next example. At a distance of 7.5 times 10 to the -1 meters from a small charged object, the electric field strength is 2.1 times 10 to the 4 newtons per coulomb. So in the last question over here, we had a charge that was experiencing an electric force. So this is a charge that was feeling a force because it was in an already existing electric field. So the electric field and the charge, or the electric field in this problem, was not the one created by this charge. It was the one affecting this charge. In our second example, we have a different scenario. This electric field strength is the one being created by our small charged object. So we're going to use our other formula. And I think a little bit of a diagram here would probably be useful. So I have a charged object, Q. And if I go this distance from it, the electric field that it creates has a strength of that. And we want to know, how far do I have to go from this object to get to a place where the electric field strength, instead of this, would be this? Well, that second number, 4.2, you'll notice is twice as big as the first number, 2.1. So if I want to get to a place where the field strength is bigger, I'm going to have to go closer to this charge. Question is, how much closer? Maybe as an initial guess, since this number is twice what this number is, maybe I have to be twice as close. So instead of a distance of 0.75, I have to be exactly half that distance. Well, let's crunch some numbers and see if that ends up being the case. First of all, I think it would be useful to find Q here. And we have enough information provided in this first part to do that. Let's call this first location where we're measuring this first electric field, let's call that A. And this second location that we're measuring the electric field, let's call that B. So let's look at A first. I know the electric field at A. It's that. I know K, Coulomb's constant. And I know the distance away from the charge we are at A. That's that. So I should be able to solve for Q, the charge right here. Let's see if we can do that. That gives me Q is 1.3125 times 10 to the minus 6. Okay, so now let's look at point B, where we know what we want the field strength to be. We just don't know how far away that point is. And here, we're looking for the distance away. So we're looking for this radius here. Isolating for that radius or for that distance, I get that. Plugging numbers in. Gives me an answer of 0.530 meters. So that is not quite half the distance we originally had, which is what we were sort of guessing. 0.53 meters is more like somewhere around here. It's closer than we were before, but we're not quite twice as close. So why is it that we can get twice the electric field strength without going twice as close? We only have to move a little bit and we get quite a big shift in electric field strength. Well, that is because in the formula that dictates electric field strength, R is squared. So a small change in the distance r then gets squared, which magnifies it and makes it have a much bigger effect than it otherwise would. In fact, if we look at this formula and kind of do a little bit of math in our heads, I can make this side twice as big if I basically put a 1/2 in the denominator down here. Making the denominator half the size will make the whole thing twice as big. So how can I get a denominator that's half as big by changing r? Well, if I divide r not by 2, but by the square root of 2, that change will then get squared, and I'll effectively be dividing the whole denominator by 2. So multiplying r, another way to think of it, multiplying r by 1 over the square root of 2, when I take that change and I square it, I'm basically multiplying my whole denominator by 1 over 2, which effectively multiplies the electric field by 2. And indeed, you can check. If you just take this r and divide it by divide it by the square root of 2, you'll get exactly the number we came up with down there. One last thing I want to point out before we go is in this question, we didn't really use any positive or negative signs. We just used this formula with the magnitude of the charge and the magnitude of the electric field. Whereas up here, positive and negatives were really important. We had a negative in our answer. We put a positive number in. That meant something was left. And that's because this formula has vector hats in it. So it should be used with positives and negatives because you can use them to tell you the direction. Whereas this formula does not have vector hats. So you're not going to be able to get the formula to tell you direction. So you should not put positives and negatives in it. And that idea can actually be carried back to our previous page where we talked about these formulas in the first place. This formula, when you're using it, put in positive or negative numbers for Q because those will be useful in telling you the direction. This formula, although electric field is a vector, there's no vector hat on it in this formula because this formula cannot tell you the direction. So don't put in positive or negative numbers for Q there. Just put in the magnitude. And then that'll help you find the magnitude of electric field. The direction of electric field, if you're using this formula, you can find out on your own. that's all for this lesson. Hopefully it gives you the tools you need to start tackling some problems with electric fields.